Hi everyone, welcome back. So far we have covered how to set up a PDK and also, excuse me, how to um, characterize devices at high frequency. So I thought it's a good time to probably start talking about circuits. So we'll start with a very standard circuit called the cross-coupled oscillator. In this video, we'll just look at the theory and intuition behind it. And in the next one, we'll look at how to actually design it based on some design parameters, I guess, in cadence, excuse me. Okay, so let's get started. So the first thing to talk about is the startup condition for oscillation. So here I'll focus on RFIC kind of design where it's not at millimeter wave really, maybe around 10 gigahertz or also microwave and RF design. In the future, we'll look at millimeter wave versions of this oscillator, but they're very similar in concept. So that's why I thought I'll start with this. So typically two different constraints, startup conditions or two different oscillation conditions are talked about in the literature. And the first one is called Barkhausen criteria. And the second is based on this negative resistance idea. Okay. So what is Barkhausen criteria? I'm not going to talk about that in this video. So this is generally used for ring oscillators. And this one we'll use for LC oscillators. So Barkhausen criteria basically says that, okay, if you have a linear system in feedback, then the closed loop phase should be 0 degrees or some multiple of 2 pi. And then if the total closed loop gain is 1, then you can have an oscillation in that circuit, right? And also talks about instability, things like that. And negative resistance says that if you have some resistance in your LC resonator, and if you can cancel that with a negative resistance circuit, then that LC resonator should behave like an oscillator. Okay, so since we've kind of briefly talked about these two, I want to, before the control systems guys go crazy, I want to say one note, which is that both of these criteria are mathematically wrong, I would say, in fact, not rigorous, they're not even correct, right? So why? Why are they wrong? Well, I mean, we started off the whole limit cycle discussion saying that you can't have oscillators like a stable limit cycle in a linear system, right? Whereas both of these criteria, Barkhausen criteria and the negative resistance criteria, are both based on linear systems theory, right? Or linear circuit theory. So clearly they cannot define or they cannot place an oscillation condition when the condition for oscillation itself is that it can only occur in nonlinear circuits, right? So that's one big issue with it. Another issue is that Barkhausen criteria in general actually is not true. There are many exceptions that you can find to this Barkhausen criteria. And even the same, you can say the same thing actually about negative resistance as well. So just adding a negative resistance in any circuit to cancel out the resistance doesn't mean that you will get an oscillation condition, right? But we will still use them to build intuition, right? So they're still they provide some intuition. And we only use them to study what is called the startup condition, right? So essentially, okay, what do I need in a given circuit for it to start oscillating, right? To start growing at least. So typically you'll have like an LC resonator, let's say with some loss in it and some noise. And then you want to see, okay, what conditions do I need to satisfy for it to start oscillating? So there, I think it's still valid to look at these kind of linear models because during startup, the signals are weak, right? And then the system basically is linear. So it's still okay to think about these criteria in terms of startup, but they're not accurate to analyze what is a generalized, to find a general oscillation condition. Actually, as far as I know, there is no there is no way to find out. There is no oscillation condition that exists. So you can't say, okay, if this condition is satisfied, the circuit will oscillate. In fact, in nonlinear system theory, as far as I know, it's very hard to find a limit cycle in a given system. So the way this works is kind of that, okay, people have designed certain circuits and they know that these topologies oscillate. And then now we have kind of superimposed on top of this criteria that help us understand maybe why they start oscillating, right? So just think of these criteria as sort of an intuitive approach. They're not exactly mathematically rigorous. Okay, so enough about that. So let's get started. So since we're doing cross-coupled oscillators, we'll look at the LC model and we'll use this negative resistance startup condition, right? So let's review what that is. So let's say I have some kind of an LC resonator with some loss associated with it. So we'll talk about where this comes from. I call this RP, C, and L. Then what you can say is, let me make a copy of this. So you can say, okay, even if I add some kind of a negative resistance in parallel to this, minus RP of some value, let's say it's RP in this case, then you can say, okay, this whole thing goes away, becomes an open circuit with infinite impedance in this direction, right? They both cancel each other in some sense. And you're left with this LC oscillator here, or LC resonator, and you can say, okay, this kind of starts to oscillate, right? Or this can oscillate. Okay, again, this is sort of contradicting myself from the original limit cycle video, but let's just go with it, right? So it's not accurate, but intuitive. Okay, so essentially, although this may not be accurate, it's a good way to maybe think about practical circuit design is how do I create this? So question then becomes, how do I create this negative resistance, right? How do I create this? Okay, so let's look at that. So I label that as 1, so this should be 2, okay. Cross-coupled pair. Okay, so let's say I have 2 transistors that are connected this way. Can do this for PMOS as well, but I'm just doing it for NMOS right now. This is grounded. And my question is to say, okay, if this is inside a black box, right? So I want to say, okay, what is the impedance looking into this box, right? We'll find out what that is. So the way to study this is to say, okay, you can copy paste this here. And then I can say, okay, I can connect a test current source, IT. And then I'll also look at the test voltage. So the input impedance would then be VT over IT, right? Okay. Okay. So since we said we're only going to study this for the startup condition, we know the signals are small initially. So we can use the small signal model for this. So hopefully you know what that is if you've taken a circuits course. Then the small signal model, I'm going to ignore the channel length modulation. So we'll just place 2 current sources. I'm going to treat these these transistors as 2 current sources. And we know that this current source is given by GM Vy, since this one's gate is controlled by the voltage here. So let me label that. Say this is Vy and this is Vx. Call this Vy, this is Vx. And this one's current is given by Gm Vx, right? And then I have my current source out here, IT, and the voltage across it is Vt. All right. So it's a very simple circuit, of course. All we need to do is to find out what is Vt over It, right? And it's literally two lines. So we know that Vt is Vx minus Vy, and It is nothing but Gm Vy, right? It's three current sources in series, so they must be equal. And we also have that Vx equal to minus Vy, because GmVx is equal to minus GmVy, right? Or GmVy is minus GmVx, right? Because this current source and this current source must be equal and opposite in direction, right? So substituting these three equations together, we get that Vt over It is simply minus 2 over, is let's say Zin is equal to minus 2 over Gm. It's an important value to remember. So of course you see now that this is a negative resistance, right? And I should say it's a negative small signal resistance. It's not breaking any laws of physics. And we'll see why exactly it's negative, an intuitive explanation as to why it's negative. Okay, so why is it negative? Let's do that right now, actually. So you see that, okay, so if I have, what does a resistance even mean, right? So what does a small signal resistance mean? So if I have some black box, and I apply, let's say, a current source to this, I test and look at the voltage across it, we test. Then I know that when IT, small signal, so DIT increases. So when IT changes in, increases, DIT is positive, right? So let me write it like this. IT increases implies DIT is positive, right? If IT increases, and this is a positive resistance, then VT should also increase from Ohm's law, implies that dVT, the change in VT, is also positive, right? And a negative resistance, so negative resistance is VT would decrease. So when IT increases, VT decreases, implies that dVT is negative, and that's why dVT over dIT is a negative value, which is the small signal resistance. And that's exactly what happens here. So we see that when, we can even look at this circuit, this one. So when IT increases, we know that GmVy increases, which is the current through this increases, and GmVx should decrease, right? Because it's in the opposite direction. So that means that Vx decreases and Vy increases, which means that Vt decreases, right? So the current It has increased, but Vt has decreased, and that's why the derivative Vt over It is negative. And that's kind of happening because of this kind of cross-coupled connection that we have here, right? So when this goes up, it's pulling more current through this, and when this goes down, it's pushing more current back up that way. And that's the opposite of what you would see in a regular resistor. So that's kind of the intuitive explanation of this. Okay, so now that we've created our negative resistance, we go back to look at the parallel LC model again. So we said, okay, I have an inductor. Let's say now we take a real inductor and a real capacitor and put them in parallel. And we said, okay, this is connected to some RP. So what exactly is this RP, right? So in reality, this inductor is the one that has a resistance, and that resistance actually is in series, right? So in reality, actually, this is something like this. and we have an R series here, right? I'll actually call this RP, and C can be C, doesn't matter, and LS, right? So this is the real model. This one is a real model, and we want to find an equivalent model like this so we can place a parallel negative resistance to cancel out this guy, right? So to do an equivalent model, all we need to do is basically equate these two, right? And since the C part is the same, it doesn't matter. So all we need to do is to say that this parallel combination impedance is equal to this series combination impedance, right? And the series combination impedance is j omega Ls plus Rs, and that is equal to j omega LPRP over j omega LP plus RT, right? So this is some simple algebra. Basically, you can take this term there and then multiply it out and then equate the real and imaginary parts. And eventually you'll end up with LP equal to RS square over LS omega square plus LS. And okay, so this is what you end up with. And we can actually show that this value is much less than 1. And that's because the Q of this inductor is defined as Ls omega over Rs. So Q is kind of a metric of how much energy is stored divided by how much power is dissipated per unit cycle, right? That's actually the definition of Q. So usually for inductors in ICs, the quality factor is around 10 or so. So when you square it, which is what this value is, it's more than 100. So 1 over that would be much less than 1. So we can ignore this term. So essentially what this is saying is that the parallel inductance and series inductance are equal. And if you solve for the parallel resistance, then that will give you Ls square approximately, because we're making this assumption first, Ls square omega square over Rs. So this is also important to remember. What is the equivalent parallel resistance of an inductor with a series resistance of Rs? Right, so you can obviously see that since they're series and parallel, when the series resistance goes up, the parallel resistance goes down. The frequency goes up, this parallel resistance goes up, and so on, right? Okay, so one note I would like to make. So this equivalence is only a narrow band equivalence, right? Is only true at I should say the resonance frequency, right? Or this omega frequency, not exactly resonance frequency, but this omega. So it's only true at a specific omega. Let me say this equivalence is narrow band. Okay, so intuitively, it's very easy to see that because at DC, this circuit is equivalent to, so at DC, we have a circuit that looks like this, right? So it's a resistor, capacitor is open, inductor is short. Whereas this circuit at DC, so at DC, this is like this, it's closed. So you have a closed loop, right? Whereas at infinity, at infinite frequency, very large, very high frequency, use a different color. At omega equal to infinity, you have the opposite case, right? So the capacitor is shorted and the inductor is open. So that thing is short like that. And then in this case, you still have, it's the same actually. Like that, capacitor is short, inductor is open. And this one has a model like this, right? So intuitively, it's easy to see that at very high frequency and very low frequency, these approximations are not valid. But at some frequency, they're the same. Okay. Hopefully that makes sense. So just keep in mind that that's kind of a narrow band equivalence, right? Okay. So now we have all the pieces to put together. So we have a negative resistance, we have a parallel RLC circuit, So now we can actually look at the cross-coupled circuit model. So cross-coupled oscillator. Okay. We start with the cross-coupled pair. And then we have, let's say, an inductor and its series resistance. So this is the actual model. And then a capacitor like that, right? So that's kind of the starting point. And then we will kind of make this. So this is L, S, R, S, and some C. And we just saw how to convert this into a parallel model. Let's say at the oscillation frequency. Okay, like that. And what I can do is that, so this actually has a line of symmetry, right? And you can actually show that this oscillator will do it, will oscillate differentially. So when this current goes up, this current goes down, and so on. And because it's differential, this can be broken up into two half circuits. So I can say, okay, that capacitance is the same as two series capacitors that are each double the size, right? And then two series inductors that are each half the size, and two series resistors like this. And I have my transistors down here, again, cross coupled like this. And now what I can do is I can actually bias these transistors at connecting all of these nodes, because all of these are essentially just ground. And I connect this up to VDD, right? Okay, that's nice. VDD is the same thing as an AC ground. And since these nodes are anyway virtual ground, because it's a differential circuit that kind of oscillates like this, it's the voltage. Virtual ground, they can be connected up to an actual ground, AC ground. And I can replace that AC ground with a DC supply, constant DC supply, because that's the same thing as an AC ground, right? So redrawing all of this essentially gives us the final circuit, which looks like this. I have one parallel RLC like this, another parallel RLC here, and then my transistors. Cross coupled that way, down here. Okay, so that's the final circuit. So essentially now you see, you can trace back why this is exactly the same thing as this one. And this one we've seen now has a negative resistance looking down here, and essentially has a positive RLC circuit, positive resistance parallel RLC circuit looking up there, right? So these two are actually identical. Okay, so this is in fact the cross-coupled oscillator, right? So let's analyze this a little bit more. So if I look at, let's say, this node, and I plot what is the voltage here, the DC voltage, of course, here is VDD, right? Because this thing is VDD, and at DC, that inductor is like a line, like a short circuit. So at DC, this should be VDD, and the swing has to be about this point, right? So the oscillator oscillates like this. And this value, let's call it V peak, VP. So I'll call this VP. Okay. So this is called the voltage swing. VP is the swing. We'll try to find a value for this. Okay. So there's one issue right now, which is that when this node is swinging up, this node is swinging down, right? So if, for example, this is at Vx, then maybe I should use red. So I'll call this Vx, right? Then Vy would be going the other way. This would be Vy. So I'll call this Vy, and this is Vx. Okay, which means that when the drain is at VDD plus VP, the gate is at VDD minus VP. Okay, let's say when the gate is at VDD plus VP, the drain is at VDD minus VP. And that's a problem, right? Because we know that for this transistor to be in saturation, we need V drain minus, or VDS should be greater than VGS minus V threshold, right? So if you do some quick maths, essentially, if you say, okay, this, I can write this as an equality condition. So what is the maximum value of V peak I can have is when VGS minus VTH is equal to the drain, when they're equal, which is the same thing as VD minus VG should be equal to minus VTH. And we know that VD minus VG is nothing but VDD minus VP minus VDD plus VP would be equal to minus VTH, which means that V peak to V peak is equal to VTH, right? Which means that V peak is VTH divided by 2, right? All of this is to essentially say that if you want to avoid triode operation, which is good because the flicker noise gets worse at triode, so you don't want that. Then the maximum V peak to peak, which is 2 times the V peak, is equal to VTH. This is also an important rule of thumb to keep in mind. Okay, so that's that. All right, there's another issue with this design that we need to talk about, which is that when so you have VDD minus VP here and you have VDD plus VP here, right? So at some point, when these two signals start to become close to each other during the swinging process, the drain current here is not well defined. Right? For example, you can think, I mean, if this becomes triode, this goes close to triode or goes into triode, then the drain current becomes proportional to this value, right? To the VDS, because it becomes like a resistor. And that's why the drain current of this kind of topology is not well defined. So to actually make it well defined, what we will do is we are going to, let me actually copy this. So I'll use a fresh page. Okay, that's good. So we can erase all of this. And we also want to erase these. So to make it well defined, essentially we add tail current source here, ISS. We'll actually go back in future videos and later on during millimeter wave oscillator design, we'll go back and actually look at whether this is actually necessary or not, what kind of performance benefits it can give, how can it hurt the circuit and things like that. But for now, since we're at RFIC still sort of not going into real millimeter wave stuff, we'll keep it there. Okay, so now of course the current through both the branches is very well defined by this ISS, right? So if you go ahead and plot again what the voltages and currents look like. respect to time. So let's say this is Vx and Vy. Let's use maybe different colors for both. Vx and Vy. So we said, okay, Vy looks like sinusoidal like this, and Vx looks like a sinusoid like this, right? And then if we plot the current, Ix and Iy, so what do the currents look like? The current actually looks a bit different. So when Vx is large, current in Iy would be high, right? So that should be like this. Almost looks like a square wave. Like that. And why is that? Because I mean, current is basically being switched between this side and this side, right? So when this one is pulling all the current down, this guy is turned on, it's pulling current down. And this side, the current goes up, right? So they're kind of out of phase, and the current, if you design it correctly, at least this current should be steered like this, right? It should be driven with hard transitions. When the current is like this, the voltage, on the other hand, doesn't have these higher order harmonics that the square wave has. So this obviously is kind of a square wave, so it has all the higher order harmonics, whereas voltage doesn't, because it gets filtered out by these tanks. So the voltage is still sinusoidal, and that has some implications which we'll kind of explore in later videos. But okay, so that's what the voltage and current waveforms look like. Now we want to make it a little bit more quantitative. So we want to say, okay, what is this V peak value, right? And let's assume this current is a proper square wave. So if I have a square wave like this, that goes from +1 volts to -1 volts, then you can actually show that the fundamental component of this would have a slightly higher amplitude, right? You can decompose the square wave into Fourier series, and then the Fourier coefficient of the first harmonic, or the fundamental, would have an amplitude that is about 4/pi. So this value is about 4/pi. Once again, a rule of thumb to keep in mind. And then based on this, essentially, I think I made a mistake here. So this should not be, time should be here. So this is 0. This is 0, and this is ISS. So when the current is flowing in this direction, in this branch, there is no current in this branch. It's 0, actually. It's entirely steered in one direction. So that current completely flows into this. And in the second half of the cycle, the current flows down this way. There's no current flowing back up. So that was a mistake that I made. Okay. So now that's cleared up. So we have essentially, if we look at the relation, the similarity between these two, then you can say, okay, the fundamental current here should have, maybe let me redraw this. Let's just redraw it. Okay, so here, the current, this is T, it's kind of a square wave like this, right? So which means the fundamental component would be like this. And since this amplitude is ISS over 2, this amplitude would be ISS over 2 times 4/pi, right? So the fundamental component of the current has an amplitude of 2 ISS over pi, right? Which means that the voltage is just 2 ISS over pi, and that's flowing through entirely through this resistor because at resonance, this guy doesn't exist, right? So this one's resistance is not important. So at resonance, it's only like you have a single resistor there, and that's the RP value of each branch, right? So that's why you end up with VP equal to 2 ISS RP over pi. So that is also kind of an important relationship to keep in mind. So this will eventually, and we know that this shouldn't exceed VTH over 2. So that'll give us an idea of how much ISS we can actually use for a given RP. We'll get to the design procedure later, but these are just some equations to keep in mind. Okay, so of course we peak to peak differential should be 8 times this value, right? Because we peak to peak is twice of this, and then differential gives you another factor of 2. That makes it 8 times, right? So again, this is assuming that, keep in mind that this is assuming I is a square wave, right? Which is not exactly true. So you need to basically drive M1 and M2 completely, switch them basically to on and off states so that it drives the current as a square wave. And we'll see how to do that. So that's essentially GMRP must be much greater than 2. This is again another rule of thumb to keep in mind. Right? And this kind of enforces the transistors to drive the current with maximal switching. Okay. So that's basically the idea behind these kind of oscillators. Do a quick review before we get into design procedure, which I'll cover pretty quickly. So we started with startup condition. We said, okay, Barkhausen negative resistance, both are used. Barkhausen used for ring oscillator kind of architectures, typically a negative resistance for LC. Both are mathematically not really rigorous, but they provide some intuition, and it's still okay to use them to study the startup condition that's required for oscillation. We also said that oscillators, it's very hard to actually show that a given circuit would oscillate. You generally know based on experience, I guess, which circuits tend to oscillate. And to really get an idea of why they start oscillating, you can look at linearized models, such as these two models here, and negative resistance model is one of them. So we said, okay, if I have an RLC parallel tank, I can put a negative resistance into it, and then it should start oscillating. Again, just an intuitive picture as to why that happens. Cross-coupled pair, we looked at how to generate this negative resistance. One option is this cross-coupled pair. There are other circuits as well. In future videos, we'll look at those. Colpitt's oscillator is one of them that also produces a negative resistance, or 3-point oscillator as it's known in the literature, I guess. And we saw, okay, this gives a negative resistance of -2 over GM, which is a small signal resistance, which is okay since we're only looking at startup condition, right? And then we said, okay, if I have a parallel RL versus series RL, how to equate them. And we saw the equivalence is narrow band. And finally, we put these together to show that you can come up with this cross-coupled oscillator based on this negative resistance condition. And we showed how we can kind of go through the topology and clean it up to come up with the final topology of a cross-coupled oscillator pair. We saw the voltage swing has to be limited to VTH, the threshold voltage, in order to make sure that this doesn't go into triode region. And then lastly, we looked at the importance of adding a tail current to make sure that the DC current through both branches is well defined. And we said, okay, maybe later on we'll revisit this tail current and see whether it's actually necessary, but we went ahead with it anyways. And we said, if the drain currents are driven strongly by the GM of the transistors, then you should get a square wave for the drain currents. And when one branch is fully conducting, the other one doesn't have any current. And this kind of square wave current through the branches gets cleaned up by the LC tanks up there, and you get a voltage that's more or less purely sinusoidal, right? And then we gave some quantitative numbers, I guess, on what VP should be based on the square wave approximation. And that's kind of where we ended. So using these equations, now let us look at how we can come up with like a straightforward design procedure. Okay. So the last section is design procedure. I would say sort of algorithmic approach. Algorithmic approach. All right. So the first step. So, okay, let me say that this is based on a specified DC power consumption and low phase noise constraints. So whenever you want to design something, of course, you have to set some kind of goal, right? So that's the goal. We say, okay, we specify what the power dissipation is approximately, how much power we want to burn, and what is the phase, we want to minimize the phase noise for that given power budget, right? That's the kind of design philosophy we're going to go with this in this video, at least. When we look at millimeter wave, we may see that, okay, this is maybe not the best approach because there the limiting constraint is output power, and the design procedure, analysis, everything might be totally different, right? So we look at that in a later video, but for now, let's just say this is the procedure, that this is the constraint we want to set. Okay, so we know that the first step is set PDC. And we know that since we want low phase noise, we don't want to enter triode region. So V peak should be VTH divided by 2, right? So that's specifies what V peak is. Okay, step 2 is that ISS is equal to power dissipated divided by VDD. Right? And VDD is usually set by the process itself. So from this, you know what ISS is. So ISS is determined. Right? So that's done. V peak is also determined. That's also done. Because VTH, VDD are process dependent, right? They're constrained already. Okay. And we know that VPP is the same as VTH, which is the peak to peak. We saw that this was 4 ISS RP divided by pi, right? Which means that RP is now given by pi times VDD, VTH divided by 4 PDC. So that determines RP. Right, so now you have RP is determined. Maybe I shouldn't put a box around VP because we don't, that's not a design constraint necessarily. Right, so we want to find the value of ISS. We found that. We wanted to find the value of RP. We found that. Okay, then step 3 is the quality factor. We know is RP over L1 omega naught, and L1 is already known. Sorry, not L1. Omega naught is already known, which means that L1 is now given by RP divided by QL omega naught. And I should mention here that QL is, this is sort of predetermined approximately by the process and omega naught. Okay, so you have to basically try different inductor layouts. I already made a video on how you can parameterize on-chip inductors and transformers. So you can look at that and see, okay, you simulate different sizes and see what is the best Q you can get. It's usually around 8 to 10. So depending on the frequency, of course, but let's say it's around 8 to 10, can go up to 15 or so at lower frequency, and at millimeter wave, it can come down. But at millimeter wave, usually you don't use inductors, we'll use transmission lines instead, which we'll get into later. But it's around 8 to 10. So let's assume it's 10 or 8, and then you'll basically fit that determines what's the value of L1, right? Or yeah, LS, I guess is what we called it. Maybe I didn't name it, so we call this L1, C1, R1. Let's this also say L1, C1, R1. So that determines L1. And of course, once you have L1, C1 is also determined, right? C1 is nothing but 1 over omega naught square L1. Okay. Of course, this C1 is also includes parasitic capacitances. So you have to kind of tune this a little bit to get the right frequency, right? So you start by assuming, okay, you know what CGD, CGS, and all that is. Let's say that's approximately like 25 femtofarad or 30 femtofarad. And then you subtract that and find the C1 that's left over and that you assign. Go ahead, design the circuit, see at what frequency it's oscillating, and then tune C1 so that you get the right frequency. Okay. And then the fourth one is you choose W over L ratio to get full current steering. Right, so you make it big enough so that you have enough GM that can drive these transistors to steer the current fully to one side, right? So that you get that square wave, i.e. square wave current steering. So that gives you VPP is equal to 4 over pi ISS RT. And that's what we started with here, I guess. So make sure that, of course, W over L is large enough. Okay. So you also need to keep in mind that when you scale W over L, you also take a look at the current density, right? So we saw in one of the previous videos that JD, which is equal to IDS over W. So this should be something reasonable so that you're close to, let's say, the peak F max value, right? The optimum JD for the best F max. And that's also a constraint that you need to keep in mind. This becomes more relevant when we do millimeter wave, but it's something to keep in mind. We'll look at that when we actually do the design example, right? And then finally, once you did all this and calculation, you set these values, simulate and tune first C1 to get omega naught, and then look at the phase noise performance. And if it's not good enough, then from here you go to increase power budget and redesign if needed, right? Okay, so that's how you kind of meet for a specific power budget the best sort of phase noise performance. And if you don't have good phase noise performance, then you increase the power budget that you started with. So this is essentially very similar, almost the same as what is in, should mention that here. So this is taken from Professor Razavi's TLL book. If you want to look at it in somewhat more details, you can do it there. All right. So this is sort of the design procedure. In the next video, what we'll do is we will employ this procedure to design a 10 gigahertz cross-coupled oscillator and tune it, get the right performance. And then from there, we'll go ahead and see how to simulate its ISF and see what the ISF looks like. And we'll also look at cyclostationary ISF. So those are the 3 videos that are going to come up after this. So hopefully that was useful. We'll look at more oscillator examples in the future, but this is a good starting point. Thank you.